Imagine standing under a clear night sky, gazing up at countless stars scattered across the cosmic darkness. Each point of light you see has traveled unimaginable distances to reach your eyes, racing through the void at the fastest speed possible in our universe. This is the speed of light, a cosmic speed limit that has captivated scientists and dreamers for generations. For as long as we have understood the nature of light, we have known it moves at an incredible pace. Light travels at exactly 299,792,458 meters per second. That is roughly 300,000 kilometers per second, or about 1 billion kilometers per hour. At this speed, light can circle our entire planet 7.5 times in just 1 second. It can travel from Earth to the Moon in less than 2 seconds and reach the Sun in about 8 minutes. But what makes this speed so special? Why does light seem to hold the keys to the very structure of reality itself? The answer lies not just in how fast light moves, but in what this speed represents for the fabric of space and time. The speed of light is not merely the fastest thing we know about. It is woven into the fundamental laws that govern our universe. It appears in equations that describe energy, matter, space, and time. It sets boundaries on what is possible and what remains forever beyond our reach. No matter how advanced our technology becomes, no matter how powerful our rockets or how clever our engineering, the speed of light stands as an absolute barrier. Yet tonight, we dare to ask the impossible question: what would happen if we could somehow break through this cosmic speed limit? What if we could travel at the speed of light itself? Would time stop? Would space collapse? Would we see the universe in ways no human has ever imagined? This journey begins with understanding why light speed is so important. When Albert Einstein developed his theory of special relativity in 1905, he discovered that the speed of light is constant for all observers, no matter how fast they are moving. This simple but profound insight revealed that space and time are not separate, unchanging things. Instead, they are woven together into a single fabric called space-time, and this fabric can stretch, bend, and warp. As objects move faster and faster through space, something remarkable happens. Time begins to slow down relative to stationary observers. Distances appear to shrink. Mass seems to increase. These effects become more and more dramatic as an object approaches the speed of light. At light speed itself, these effects become infinite, creating paradoxes that challenge our understanding of reality. But perhaps most intriguingly, the speed of light connects us to every corner of the universe. When we look at distant stars and galaxies, we are not seeing them as they are now, but as they were when their light began its journey toward us. The light from some stars has traveled for millions or even billions of years to reach our telescopes. In a very real sense, looking out into space is like looking back in time. So what would it mean to travel at this cosmic speed limit? Would we become one with light itself? Would we experience the universe, as photons do, racing through space without experiencing the passage of time? Would we be able to visit every star and galaxy in what seems like an instant? Tonight, we embark on this impossible journey. We will explore what physics tells us about traveling at light speed, even though the laws of nature seem to forbid it. We will discover how time would behave, how space would appear, and what paradoxes would emerge. We will venture into the realm of pure speculation, guided by the best scientific understanding we have today. The speed of light has been humanity's ultimate horizon since we first began to understand the cosmos. It represents both a boundary and a dream, a limit that defines what is possible, while inspiring us to imagine what lies beyond. As we begin this exploration, remember that we are not just talking about speed. We are talking about the very nature of existence itself, about time and space, and matter and energy, about the deepest mysteries that surround us every day. The universe holds its secrets closely, but through science and imagination, we can begin to glimpse what might happen if we could race through the cosmos at the speed of light itself. This is our journey into the impossible, our exploration of the ultimate speed, our attempt to understand what it might mean to travel as fast as light itself travels. To truly understand what would happen if we could travel at the speed of light, we must first appreciate what this speed really means and why it holds such a special place in the laws of physics. The speed of light in a vacuum is exactly 299,792,458 meters per second. Scientists often round this to 300 million meters per second, or 300,000 kilometers per second, for simplicity. This number is not just fast, it is the fastest speed at which any information or energy can travel through the universe. But why this particular speed? What makes light so special? The answer lies in understanding what light actually is. Light is a form of electromagnetic radiation, the same type of energy that includes radio waves, microwaves, X-rays, and gamma rays. All of these forms of electromagnetic energy travel at exactly the same speed through empty space. This speed is built into the very structure of space and time itself. Think of it this way. Imagine you are in a car, driving down a highway. If you throw a ball forward while driving, someone standing on the side of the road would see the ball moving at the speed of your car plus the speed of your throw. This makes perfect sense in our everyday world. But light behaves very differently. If you shine a flashlight forward while driving, the light does not travel at the speed of your car plus the speed of light. Instead, both you and the person standing on the roadside would measure the light as moving at exactly the same speed. This seems impossible, but it is one of the most thoroughly tested facts in all of physics. This strange behavior of light led Albert Einstein to a revolutionary conclusion in 1905. He realized that space and time are not fixed, unchanging things. Instead, they can stretch and compress to ensure that light always travels at the same speed for every observer. This insight became the foundation of his special theory of relativity. Einstein showed us that the speed of light is not just the speed of light. It is the speed at which cause and effect can travel through the universe. It is the speed that connects space and time into a single, unified fabric. It is the cosmic speed limit that nothing with mass can ever reach or exceed. When we say nothing can travel faster than light, we mean nothing that carries information or energy. There are some phenomena that can appear to move faster than light, like the spot of a laser pointer swept across the surface of the moon, or the expanding edge of a shadow. But these are not real objects carrying energy from one place to another. They are patterns or effects that can move quickly without violating the cosmic speed limit. The speed of light also determines how we experience the universe around us. Every star you see in the night sky is showing you its past, not its present. The sun you see during the day is actually the sun as it was 8 minutes and 20 seconds ago, because that is how long light takes to travel from the sun to Earth. The nearest star beyond our sun is Proxima Centauri, located about 4.25 light years away. This means the light from Proxima Centauri that reaches your eyes tonight actually left that star over 4 years ago. When you look at the Andromeda Galaxy, you are seeing light that began its journey over 2.5 million years ago, when early human ancestors were just beginning to use stone tools. This connection between light speed and time creates a fascinating perspective on the universe. The faster you travel through space, the slower you move through time, at least from the perspective of someone who is not traveling with you. This effect is called time dilation, and it becomes more pronounced as you approach the speed of light. For most of human history, we thought time was absolute and universal. We assumed that a second was a second for everyone, everywhere, always. But Einstein showed us that time is relative. It depends on how fast you are moving and how strong the gravitational field around you happens to be. At everyday speeds, these effects are incredibly tiny. If you spend your entire life in a jet airplane, you would age only a few microseconds less than someone who stays on the ground. But as speeds approach the speed of light, these effects become dramatic and impossible to ignore. The speed of light also appears in one of the most famous equations in all of science. Einstein's equation E equals mc squared tells us that mass and energy are interchangeable. The c in this equation represents the speed of light, and the fact that it is squared means that even a tiny amount of mass contains an enormous amount of energy. This equation explains why stars shine, why nuclear power works, and why it becomes harder and harder to accelerate objects as they approach light speed. As you push an object faster and faster, more and more of your energy goes into increasing its relativistic mass rather than its speed. To actually reach the speed of light would require infinite energy, which is why physicists say it is impossible for anything with mass to travel at light speed. But what if we could somehow overcome this limitation? What if we could find a way to reach this cosmic speed limit? The implications would be far more strange and wonderful than most people imagine. The very nature of time, space, and reality would transform in ways that challenge our deepest assumptions about how the universe works. But the story of light speed goes much deeper than just physics equations and cosmic speed limits. Throughout history, humans have been fascinated by light and its properties. Ancient philosophers wondered whether we see by light coming from our eyes or by light entering them. They debated whether light traveled instantly or took time to move from place to place. It was not until the 1600s that scientists began to measure the speed of light. The first successful attempt came from a Danish astronomer named Ole Rømer in 1676. He was studying the moons of Jupiter when he noticed something peculiar. The timing of eclipses seemed to change depending on whether Earth was moving toward or away from Jupiter in its orbit. Rømer realized that this was because light took time to travel across the solar system. When Earth was farther from Jupiter, the light from Jupiter's moons had to travel a greater distance, causing the eclipses to appear delayed. This was the first evidence that light had a finite speed, though Rømer's calculation was not very accurate by modern standards. Over the next few centuries, scientists developed more precise methods for measuring light speed. They used rotating mirrors, spinning wheels with gaps, and eventually laser interferometry to pin down the exact value. Each measurement revealed that light speed was not just fast, but remarkably constant under all conditions. This consistency is what makes the speed of light so fundamental to physics. Unlike other speeds in nature, which can vary depending on conditions, the speed of light in a vacuum never changes. It is the same whether the light comes from a candle, a laser, or a distant star. It is the same whether you are standing still or moving at tremendous speeds. This constancy has profound implications for how we understand reality. If light speed is always the same for every observer, then other things must change to accommodate this fact. Specifically, time and space must be flexible, able to stretch and compress as needed to keep light speed constant. Consider what happens when you observe a spacecraft traveling at 90% the speed of light. From your perspective, time aboard that spacecraft appears to slow down dramatically. Clocks on the spacecraft tick more slowly. The people inside seem to move in slow motion. This is not an illusion or a trick of perception. Time really is running more slowly for them compared to you. But here is the remarkable part. From the perspective of the people on the spacecraft, their time is running normally. Their clocks tick at the usual rate. They move and think and live exactly as they always have. Instead, they see your time as running slowly. They see your clocks ticking more slowly than theirs. Both perspectives are equally valid. There is no absolute reference frame that determines which clock is really running slowly. This is what Einstein meant when he said that all motion is relative. The effects of traveling at high speeds are symmetric. Each observer sees the other's time as dilated. This symmetry breaks down only when one observer changes speed or direction. If the spacecraft turns around and comes back to Earth, the people on board will have aged less than those who stayed behind. This is the famous twin paradox, which has been confirmed experimentally using atomic clocks on fast-moving airplanes. The speed of light also determines the relationship between energy and momentum. In everyday life, we think of these as separate quantities. A moving car has kinetic energy and momentum, and we can calculate each independently. But as speeds approach, the speed of light, energy, and momentum become intimately connected. At light speed itself, this relationship becomes even more extreme. Photons, the particles of light, have energy and momentum but no mass. They exist in a state that is impossible for any massive object to achieve. They are pure energy in motion, traveling at the cosmic speed limit because they have no choice. Having no mass, they cannot travel at any other speed. This is why reaching light speed is impossible for anything with mass. As you accelerate toward light speed, your relativistic mass increases without limit. The energy required to accelerate you further also increases without limit. You would need infinite energy to reach light speed, which is clearly impossible. Yet photons achieve this impossible speed effortlessly. They are created already traveling at light speed and can never slow down or speed up. From their perspective, if we can even use that term, they travel from their source to their destination instantaneously. A photon from a distant galaxy experiences no passage of time during its billion-year journey to Earth. This gives us a hint of what it might be like to travel at light speed. If you could somehow achieve this impossible speed, you might experience the entire universe as a single moment. Every journey, no matter how far, would seem to take no time at all. The vast cosmos would collapse into a single point of experience. The speed of light also connects to some of the deepest mysteries in physics. Why does light travel at this particular speed and not faster or slower? Why is the speed of light the same as the speed of causality, the speed at which cause and effect propagate through space? These questions touch on the fundamental nature of reality itself. Some physicists believe that the speed of light is determined by the properties of empty space itself. Space is not truly empty, but filled with quantum fields that give it structure and properties. The speed of light might be set by how quickly disturbances can propagate through these fundamental fields. Others suggest that the speed of light is related to the dimensionality of space. In our three-dimensional world, the speed of light has the value we observe. In universes with different numbers of spatial dimensions, light might travel at different speeds or behave in completely different ways. Understanding the speed of light is just the beginning of our journey. As we explore what might happen if we could travel at this ultimate speed, we will discover that the universe is far stranger and more beautiful than our everyday experience suggests. The speed of light is not just a number or a limit. It is a doorway to understanding the deepest mysteries of existence itself. The speed of light shapes everything we know about the cosmos. It determines how long it takes for news to travel from one star to another. It sets the scale for how large the observable universe can be. It governs the fusion reactions that power stars and the radioactive decay that heats the Earth's core. Without the finite speed of light, the universe would be a very different place. Information could travel instantly across any distance. There would be no delay between cause and effect, no time for light to travel from distant stars, no way to look back in time by looking out into space. The cosmic web of galaxies and the evolution of the universe itself depend on light having a finite, constant speed. Time is perhaps the most mysterious aspect of our existence. We experience it flowing steadily forward, second by second, minute by minute, carrying us from past to future in an endless stream. Yet when we begin to travel at speeds approaching the speed of light, time reveals its true nature as something far more flexible and strange than we ever imagined. The phenomenon of time dilation is one of the most counterintuitive predictions of Einstein's special relativity, yet it has been confirmed by countless experiments and observations. As you travel faster through space, time literally slows down for you relative to observers who are not moving with you. This is not a mechanical effect of clocks running slowly. Time itself stretches and dilates. To understand what happens to time as we approach light speed, imagine yourself aboard a spacecraft gradually accelerating toward this cosmic speed limit. At first, when your speed is only a small fraction of light speed, the effects are barely noticeable. Time runs just slightly slower for you than for observers back on Earth. The difference might be measured in microseconds over the course of years. But as your speed increases to 50% of light speed, something remarkable begins to happen. Time aboard your spacecraft starts running noticeably slower compared to Earth time. A journey that takes 1 year according to your onboard clocks might correspond to about 1 year and 2 months as measured by Earth observers. The effect is still relatively small, but it is becoming significant. When you reach 90% of light speed, the time dilation effect becomes dramatic. Your onboard clocks show that a year has passed, but observers on Earth measure over 2 years passing during the same journey. Time has stretched by more than a factor of 2. From Earth's perspective, everything aboard your spacecraft appears to be happening in slow motion. As you approach 99% of light speed, the time dilation becomes extreme. A single year aboard your spacecraft corresponds to over 7 years on Earth. You age 1 year while the Earth ages 7. This is not science fiction, but a direct consequence of the structure of space-time itself. At 99.9% of light speed, the ratio becomes even more extreme. 1 year for you equals over 22 years on Earth. At 99.99% of light speed, the ratio approaches 1 year for you to over 70 years on Earth. The closer you get to light speed, the more extreme the time dilation becomes. What would it feel like to experience this stretching of time? From your perspective aboard the spacecraft, absolutely nothing would seem unusual. Your heart would beat at its normal rate. Your thoughts would proceed at their usual pace. Your watch would tick off seconds in the familiar rhythm. The flow of time would feel completely normal to you. The strangeness would only become apparent when you compared your experience to the outside world. If you could somehow observe Earth during your high-speed journey, you would see everything there happening in fast forward. People would seem to move quickly, seasons would change rapidly, and years would flash by like days. This leads us to one of the most profound implications of time dilation. As your speed approaches the speed of light, time dilation approaches infinity. At exactly light speed, time would be stretched by an infinite factor. From the perspective of outside observers, your time would stop completely. A single moment aboard your light-speed spacecraft would last forever as measured by the rest of the universe. But what would you experience during this infinitely dilated moment? This is where physics enters truly mysterious territory. From your perspective, traveling at light speed, the entire universe would seem to flash by in an instant. Distances would contract to zero, and you would travel from any starting point to any destination instantaneously. This creates a fascinating paradox. From the outside universe's perspective, you would be frozen in time, taking forever to complete your journey. But from your perspective, you would complete any journey, no matter how far, in zero time. These two descriptions of the same event seem contradictory, yet both are equally valid according to the principles of relativity. Time dilation affects not just mechanical clocks, but all physical processes. If you were traveling at 99% of light speed, your biological processes would slow down by the same factor as your clocks. Your heart rate, brain activity, aging process, and every chemical reaction in your body would proceed more slowly, as measured by outside observers. This means that high-speed travel could theoretically allow for a form of time travel into the future. If you traveled to a distant star at 99% of light speed, you might experience the journey as taking only a few months, while decades or centuries pass on Earth. When you return, you would find that Earth has aged far more than you have. You would have traveled into Earth's future. The mathematics of time dilation is governed by what physicists call the Lorentz factor, named after Dutch physicist Hendrik Lorentz. This factor determines how much time stretches at different speeds. At low speeds, the factor is nearly 1, meaning time dilation is negligible. But as speed approaches light speed, the Lorentz factor approaches infinity. This mathematical behavior explains why nothing with mass can reach light speed. As you approach light speed, the Lorentz factor grows without bound. This means that time dilation becomes infinite, length contraction becomes complete, and the energy required for further acceleration becomes infinite. These infinities are physics telling us that light speed is absolutely unreachable for massive objects. Yet light itself travels at this forbidden speed. How is this possible? The answer lies in the fact that photons have no mass. For massless particles, the equations of relativity work differently. Photons must travel at light speed and can travel at no other speed. They exist in a realm where time and space have no meaning in the way we usually understand them. From a photon's perspective, if we can even use that term, it is created and absorbed in the same instant, regardless of how far it travels. A photon from a star, billions of light years away, experiences no passage of time during its journey to Earth. The billions of years we measure for its journey are experienced as zero time by the photon itself. This gives us another hint about what it might be like to travel at light speed. If you could somehow achieve this impossible speed, you might experience something like what a photon experiences. The journey from any point to any other point in the universe would take zero time from your perspective. The entire cosmos would be accessible instantaneously. But the infinities that appear in the mathematics of light speed travel suggest that something more fundamental is happening. Perhaps at light speed, the ordinary concepts of time and space break down completely. Perhaps consciousness itself would be transformed in ways we cannot imagine. Time dilation also has profound implications for our understanding of simultaneity. Events that appear simultaneous to one observer may not be simultaneous to another observer moving at high speed. This relativity of simultaneity means that there is no universal now that applies throughout the universe. If you were traveling at high speed toward a distant star, events on that star would appear to happen earlier than they would to someone at rest. Conversely, events behind you would appear to happen later. This effect becomes more pronounced as your speed increases, and at light speed, it would become infinite. The stretching of time near light speed also affects how you would perceive the universe around you. Light from stars ahead of you would be blue shifted to higher frequencies, while light from stars behind you would be red shifted to lower frequencies. The familiar patterns of constellations would distort as the geometry of space-time itself warped around your high-speed motion. As we contemplate the implications of time dilation at light speed, we begin to see how profoundly different the universe would appear to a light-speed traveler. Time, which seems so fundamental and absolute in our everyday experience, reveals itself to be flexible and relative. The faster we move through space, the slower we move through time, until at light speed, time itself might cease to have meaning. Understanding time dilation is crucial for grasping what might happen if we could travel at light speed. It shows us that speed through space and the passage of time are intimately connected, two aspects of a deeper reality that Einstein called space-time. As we continue our exploration of light-speed travel, we will discover that space itself is just as malleable as time, stretching and contracting in ways that challenge our most basic assumptions about the nature of reality. While time dilation captures much of our attention when thinking about high-speed travel, space itself undergoes equally dramatic transformations as we approach the speed of light. Just as time stretches and slows, space contracts and shrinks in ways that fundamentally alter the geometry of the universe around a high-speed traveler. Length contraction, also known as Lorentz contraction, is the complementary phenomenon to time dilation. As an object moves faster and faster through space, it becomes shorter and shorter along the direction of its motion. This is not a mechanical compression due to air resistance or physical forces. The object literally becomes shorter as measured by outside observers, while the fabric of space itself contracts. To understand how length contraction works, imagine observing a spacecraft accelerating toward the speed of light. When the spacecraft is at rest or moving slowly, it appears to have its normal length. Perhaps it measures 100 meters from nose to tail. But as the spacecraft begins moving at significant fractions of light speed, something strange happens to its appearance. At 50% of light speed, the spacecraft would appear to shrink to about 87% of its original length. What was once a 100-meter spacecraft now appears to be only 87 meters long to a stationary observer. The spacecraft has become noticeably shorter, though the effect is not yet dramatic. As the spacecraft reaches 90% of light speed, the contraction becomes much more pronounced. The 100-meter spacecraft now appears to be only about 44 meters long. It has shrunk to less than half its original length. The faster the spacecraft travels, the more compressed it becomes along its direction of motion. At 99% of light speed, the spacecraft appears to be just 14 meters long, compressed to barely 1/7 of its original size. At 99.9% of light speed, it would appear to be less than 4.5 meters long. The closer the spacecraft gets to light speed, the more extreme the contraction becomes. What makes this phenomenon particularly fascinating is that the contraction only occurs along the direction of motion. If the spacecraft is traveling from left to right, it becomes shorter from front to back, but maintains its original height and width. A spherical object would appear flattened into an ellipse, then into an increasingly thin disk, as its speed approaches light speed. From the perspective of someone aboard the contracting spacecraft, nothing seems unusual about their own ship. The corridors appear to have their normal length, the rooms their usual dimensions. The crew members maintain their normal height and width. To them, the spacecraft has not contracted at all. Instead, they observe the universe outside contracting around them. This reciprocal nature of length contraction mirrors the reciprocal nature of time dilation. Just as each observer sees the other's time as dilated, each observer sees the other's space as contracted. There is no absolute reference frame that determines which lengths are really contracted. The effect is symmetric and depends entirely on the relative motion between observers. As speeds approach the speed of light, length contraction approaches an extreme limit. At exactly light speed, an object would contract to zero length along its direction of motion. It would become infinitely thin, a two-dimensional sheet with no thickness whatsoever. This mathematical singularity is another indication that light speed is unreachable for objects with mass. But what would it be like to experience this extreme contraction of space? If you could somehow travel at light speed, distances in the direction of your travel would shrink to nothing. A journey to the nearest star, 4.25 light years away, would involve crossing zero distance from your perspective. the entire universe would collapse to a single point along your direction of motion. This creates another fascinating paradox. From the perspective of outside observers, your light speed journey would take an infinite amount of time, because time dilation would stop your clocks completely. But from your perspective, the journey would cross zero distance because length contraction would shrink all distances to nothing. How can an infinite time and zero distance both describe the same journey? The answer lies in recognizing that space and time are not separate entities but aspects of a unified space-time continuum. Length contraction and time dilation are two sides of the same coin, both arising from the fundamental structure of space-time itself. As you approach light speed, space contracts in the direction of motion while time dilates, maintaining the consistency of the physical laws. Length contraction also affects how light behaves for a high-speed traveler. Light coming from ahead of you would be blue shifted to higher frequencies because you are racing toward its source. Light coming from behind would be red shifted to lower frequencies because you are racing away from its source. The familiar colors of stars would shift dramatically as your speed increases. At very high speeds, this Doppler effect becomes extreme. Stars ahead of you might shift from visible light into ultraviolet, X-rays, or even gamma rays. Stars behind you might shift from visible light into infrared, microwaves, or radio waves. The familiar appearance of the night sky would transform completely as you approach light speed. The contraction of space also affects the apparent distribution of objects in the universe. Stars that appear spread out across the sky when you are at rest would seem to crowd together in the direction of your motion as you speed up. The entire universe would appear to compress into a smaller and smaller cone ahead of you, while the region behind you would seem nearly empty. This compression would become more and more extreme as you approach light speed. Eventually, the entire visible universe would appear to shrink into a narrow beam directly ahead of you. All the stars, galaxies, and cosmic structures would seem to converge into a single bright point of light in the direction of your travel. The mathematics governing length contraction is the same Lorentz factor that governs time dilation. This is not a coincidence but a reflection of the deep unity between space and time. The factor by which lengths contract is exactly the same as the factor by which time dilates. This mathematical relationship ensures that the speed of light remains constant for all observers. Understanding length contraction helps explain why the speed of light is such a fundamental barrier. As your speed approaches light speed, the energy required to accelerate you further increases without limit. This happens partly because your relativistic mass increases, but also because the space you need to traverse contracts towards zero. The universe itself resists your attempts to reach light speed. From a practical standpoint, length contraction would have profound effects on any spacecraft attempting to travel at relativistic speeds. The engineering challenges would be enormous. How do you design a spacecraft that can function normally for its crew while appearing highly contracted to outside observers? How do you maintain structural integrity when different parts of the ship experience different degrees of contraction? These questions become even more complex when we consider that length contraction affects not just the overall dimensions of objects but every aspect of their internal structure. The spacing between atoms would contract, the dimensions of electronic circuits would shrink, and even the wavelengths of light inside the spacecraft would be affected. Yet from the crew's perspective, none of this would be noticeable. Their measuring devices would contract by the same factor as everything else, so all their measurements would appear normal. They would have no way to detect their own length contraction without comparing themselves to objects that are not traveling with them. The phenomenon of length contraction also has implications for our understanding of solid matter. We usually think of solid objects as having fixed, definite shapes and sizes. But relativity shows us that shape and size are not absolute properties of objects. They depend on the motion of the observer. An object can be simultaneously long and short, depending on who is measuring it. This relativity of spatial dimensions extends to more complex geometries as well. A sphere moving at high speed appears as an ellipsoid to stationary observers. A cube becomes a rectangular prism. More complex shapes undergo correspondingly complex distortions. The familiar Euclidean geometry of everyday experience gives way to the more exotic geometry of relativistic spacetime. As we contemplate traveling at light speed, length contraction reminds us that space itself is not the fixed, immutable stage that it appears to be in our everyday experience. Space is dynamic, flexible, and observer-dependent. It can stretch and contract, bend and warp, in response to motion and gravity. The universe is far stranger and more malleable than our intuition suggests. Length contraction, together with time dilation, reveals the profound interconnectedness of space and time. They are not separate aspects of reality, but unified components of space-time. As we move faster through space, we automatically move slower through time, and the distances we perceive automatically contract. These effects are not separate phenomena, but different aspects of a single, deeper truth about the nature of reality. In our journey toward understanding what it would be like to travel at the speed of light, length contraction shows us that the very notion of distance becomes problematic at such extreme speeds. When all distances contract to zero, when the entire universe shrinks to a point, the usual concepts of space and location lose their meaning. We begin to see hints of the profound transformation of reality that might occur at the cosmic speed limit. The speed of light stands as the ultimate barrier in our universe, a cosmic speed limit that seems absolute and unbreakable. Yet throughout history, humans have consistently found ways to overcome barriers that once seemed impossible to cross. We broke the sound barrier, escaped Earth's gravity, and split the atom. This naturally leads us to wonder whether the light barrier might someday fall as well. To understand why breaking the light barrier presents such extraordinary challenges, we must first appreciate what makes it fundamentally different from other barriers we have conquered. The sound barrier exists because of the properties of air and other materials. It can be broken because sound is simply a wave moving through a medium, and objects can move faster than these waves travel. But the light barrier is woven into the very fabric of space-time itself. It is not just the speed at which light travels, but the speed at which causality itself propagates through the universe. It is the speed that connects space and time, matter and energy, cause and effect. Breaking the light barrier would not simply mean going faster than light. It would mean violating some of the most fundamental principles that govern reality. The mathematical equations of special relativity paint a stark picture of what happens as objects approach light speed. As velocity increases toward the speed of light, several quantities grow without limit. The energy required for further acceleration approaches infinity. The relativistic mass of the object approaches infinity. Time dilation approaches infinity. These infinities are not mere mathematical curiosities, but physical barriers that prevent massive objects from reaching light speed. Consider what it would take to accelerate even a single proton to the speed of light. A proton has an incredibly tiny mass, about 1.67 times 10 to the negative 27 kilograms. Yet accelerating this impossibly small particle to light speed would require infinite energy. Not just a very large amount of energy, but literally infinite energy. The entire energy content of the universe would not be sufficient. This energy requirement grows exponentially as speed approaches light speed. To accelerate a 1 kilogram mass to 90% of light speed would require about 2.3 times 10 to the 17th joules of energy. That is roughly the amount of energy the sun produces in 6 seconds. To reach 99% of light speed would require 10 times more energy. To reach 99.9% would require over 30 times the 90% energy requirement. The pattern is clear and relentless. Each step closer to light speed demands exponentially more energy. The final approach to exactly light speed requires infinite energy, making it absolutely impossible for any massive object to achieve. This is not a limitation of our technology or engineering capabilities. It is a fundamental law of nature. But what if we could somehow overcome this energy barrier? What if we possessed infinite energy, or discovered some way to circumvent the usual rules of relativity? Would it be possible to push through the light barrier into the realm of faster than light travel? The answer leads us into some of the strangest territory in all of physics. If an object with mass could somehow exceed the speed of light, the mathematics of relativity would yield impossible results. The Lorentz factor, which governs time dilation and length contraction, would become imaginary rather than real. Time dilation would no longer make physical sense. Length contraction would produce meaningless results. The very equations that describe the behavior of space and time would break down completely. Some physicists have speculated about hypothetical particles called tachyons that would always travel faster than light, just as normal particles always travel slower than light. These theoretical particles would have imaginary mass and would exist in a realm where faster speeds require less energy rather than more. But no tachyons have ever been detected, and their existence would create serious problems for causality and the logical structure of the universe. The problems with faster-than-light travel go beyond mere mathematical difficulties. They strike at the heart of cause and effect itself. In a universe where information or objects could travel faster than light, it would be possible to send signals into the past. This would create logical paradoxes that seem to make the universe inconsistent with itself. Imagine you could send a message faster than light to a distant location, and someone there could send a faster-than-light reply back to you. Due to the relativity of simultaneity, under certain conditions this exchange could result in you receiving the reply before you sent the original message. You could literally receive an answer before asking the question. Such violations of causality would undermine the logical structure of reality. If effects could precede their causes, then the universe would become unpredictable and potentially contradictory. The past could be changed, creating paradoxes that seem to make consistent reality impossible. Most physicists believe that nature must have some mechanism to prevent such violations of causality. Yet the light barrier might not be as absolute as these arguments suggest. Modern physics has revealed several phenomena that seem to involve faster-than-light effects, though none actually violate the fundamental prohibition against faster-than-light information transfer. Quantum entanglement allows instantaneous correlations between distant particles, but these correlations cannot be used to send information faster than light. The expansion of space itself can carry distant galaxies away from us, at speeds exceeding the speed of light. But this is not motion through space, but rather the expansion of space itself. The galaxies are not moving faster than light through space, but space is expanding between them at such a rate that their recession speed exceeds light speed. This does not violate relativity because no information travels between the galaxies at faster than light speeds. There are also theoretical concepts that might allow faster than light travel without violating the fundamental principles of relativity. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, would work by contracting space in front of a spacecraft and expanding space behind it. The spacecraft itself would never exceed light speed through space, but the warping of space around it could carry it faster than light relative to distant objects. Such exotic propulsion concepts require materials with negative energy density, something that may not exist in nature. They also require enormous amounts of energy, possibly exceeding the mass energy of entire stars. Even if they are theoretically possible, they remain far beyond any conceivable technology. Wormholes represent another theoretical possibility for effectively faster than light travel. These hypothetical tunnels through space-time could connect distant regions of the universe, allowing travel between them without crossing the intervening space. A journey through a wormhole might take less time than light would take to travel the same distance through normal space. But wormholes, if they exist at all, would likely be highly unstable and would collapse before anything could pass through them. Keeping a wormhole open would probably require exotic matter with properties that may be impossible to achieve. Even traversable wormholes might not allow true faster-than-light travel, but rather shortcuts through the geometry of space-time. The quantum vacuum itself presents intriguing possibilities for circumventing the light barrier. The vacuum is not truly empty, but filled with quantum fluctuations that give it structure and properties. Some theories suggest that these quantum effects might allow for faster-than-light phenomena under extremely exotic conditions. Quantum tunneling allows particles to pass through energy barriers that should be insurmountable according to classical physics. In certain experiments, quantum tunneling appears to occur faster than light, though the interpretation of these results remains controversial. The particles do not travel faster than light in the usual sense, but the quantum process itself seems to transcend the usual speed limitations. However, all of these phenomena share a common feature. None of them allows for the faster-than-light transmission of information in a way that would violate causality. The universe seems to protect itself against causal paradoxes through various mechanisms that prevent true violations of the light-speed barrier for information transfer. The light barrier may ultimately be more flexible than originally thought, but in ways that preserve the logical consistency of the universe. Space and time themselves might be manipulated to achieve effective, faster-than-light travel, without violating the fundamental prohibition against faster-than-light motion through space. As we contemplate the possibility of breaking the light barrier, we must consider not just the tremendous technical challenges involved, but the profound implications for our understanding of reality. The speed of light is not just a speed limit, but a fundamental organizing principle of the universe. Breaking it might require not just new technology, but a new understanding of the very nature of space, time, and causality. Whether the light barrier can ever be broken remains one of the greatest open questions in physics. The mathematical infinities that arise at light speed suggest that nature has built an absolute prohibition into the structure of reality itself. Yet the universe has surprised us before with its flexibility and subtlety. Perhaps the light barrier, like other barriers before it, will eventually yield to human ingenuity and determination. Until then, the speed of light remains our cosmic horizon, the ultimate boundary that defines what is possible and what lies forever beyond our reach. It reminds us that the universe operates according to principles deeper and more subtle than our everyday experience suggests, and that some limits may be built into the very foundation of existence itself. When we venture into the realm of light-speed travel, we enter a landscape filled with paradoxes that challenge our most basic assumptions about reality. These are not mere thought experiments or mathematical curiosities, but fundamental contradictions that arise when we push the laws of physics to their absolute limits. Understanding these paradoxes helps us grasp why light speed represents such a profound boundary in our universe. The most famous of these paradoxes is the twin paradox, which illustrates the strange nature of time at relativistic speeds. Imagine two identical twins, Alice and Bob. Alice remains on Earth while Bob travels to a distant star at 99% of the speed of light. From Earth's perspective, the journey takes many years, during which Bob ages very slowly due to time dilation. When he returns, Bob finds that he has aged only a few years while Alice has aged decades. But here is where the paradox becomes apparent. From Bob's perspective during the journey, he is at rest, and Alice is moving away from him at 99% of light speed. According to the principles of relativity, Bob should see Alice's time as dilated, meaning Alice should age more slowly than Bob. When they reunite, Alice should be younger than Bob, not older. Both perspectives seem equally valid, yet they lead to contradictory conclusions. The resolution of this paradox lies in recognizing that the situation is not perfectly symmetric. Bob must accelerate to reach his high speed, travel at constant velocity, then decelerate and accelerate again to return to Earth. During these acceleration phases, Bob is no longer in an inertial reference frame, and the symmetry of the situation breaks down. The twin who experiences acceleration is the one who ages less. This has been confirmed experimentally using atomic clocks on airplanes and spacecraft. But what happens if we push this scenario to the extreme of light speed travel? If Bob could somehow travel at exactly the speed of light, time dilation would become infinite. From Earth's perspective, Bob's time would stop completely. He would be frozen in a single moment that lasts forever. Yet from Bob's perspective, the journey would take zero time due to infinite time dilation. The entire trip, no matter how far, would be instantaneous. This creates a deeper paradox. How can the same journey take both infinite time and zero time? How can Bob be simultaneously frozen in time and moving instantaneously across space? The mathematical infinities that appear at light speed suggest that our ordinary concepts of time and motion break down completely at this cosmic boundary. Another profound paradox emerges when we consider the relativity of simultaneity at light speed. In Einstein's relativity, events that appear simultaneous to one observer may not be simultaneous to another observer moving at high speed. This effect becomes more pronounced as speed increases, and at light speed, it would become infinite. If you could travel at light speed toward a distant star, events on that star would appear to happen infinitely far in the past from your perspective. Conversely, events behind you would appear to happen infinitely far in the future. The normal flow of time from past to future would be completely disrupted. Past, present, and future would lose their usual meaning. This leads to the causality paradox. If you could travel faster than light, you could potentially arrive at your destination before you left your starting point, at least from the perspective of certain observers. This would allow you to witness events before their causes, or even to interfere with events in such a way that you prevent your own departure. the logical consistency of the universe would be threatened. Consider a specific example. Suppose you could travel faster than light to a star 10 light years away, arriving there in 5 years as measured by Earth clocks. From the perspective of the star system, due to the relativity of simultaneity, you might arrive there 5 years before you left Earth. You could then send a conventional radio signal back to Earth, warning yourself not to make the trip. This would create a logical contradiction that seems to make the universe inconsistent with itself. The grandfather paradox takes this reasoning to its logical extreme. If faster than light travel allowed you to travel into the past, you could theoretically prevent your own birth by interfering with your ancestors. But if you were never born, how could you have traveled back in time to interfere? The paradox creates a logical loop that has no consistent resolution. Some physicists have proposed that the universe might protect itself against such paradoxes through what is called the Novikov self-consistency principle. This principle suggests that the universe would somehow conspire to prevent any actions that would create logical contradictions. If you tried to prevent your own birth, something would inevitably go wrong with your plan, ensuring that events unfold in a self-consistent manner. But this raises its own paradoxes. If the universe can prevent logical contradictions, does this mean that free will is an illusion? Are we constrained to act only in ways that maintain the consistency of space-time? The implications are profoundly disturbing for our understanding of choice and causality. At light speed itself, these paradoxes become even more extreme. The concept of simultaneity becomes completely meaningless. There is no consistent way to define what events are happening now for a light speed observer. The usual temporal ordering of events breaks down entirely. Past and future lose their distinction. This connects to another paradox involving the nature of consciousness at light speed. Our thoughts, our awareness, our very sense of existence depend on the flow of time. Neural processes in our brains require time to occur. Chemical reactions need time to proceed. Even the most basic physical processes that support life require temporal sequences. But at light speed, time would stop from the perspective of outside observers. Would consciousness be possible in a state where time has no meaning? Could you think, feel, or experience anything during a light speed journey? Or would consciousness itself cease to exist at the cosmic speed limit? These questions probe the deepest mysteries of mind and reality. The information paradox presents another layer of complexity. Information, like energy and matter, seems to be subject to relativistic effects. As you approach light speed, the information content of your brain, your memories, your very identity would be subject to the same infinite time dilation that affects everything else about you. From an outside perspective, this information would be frozen, unable to change or evolve. But from your perspective, the information would need to somehow function normally to support consciousness and thought. How can the same information be simultaneously frozen and active? This paradox suggests that the nature of information itself might be more mysterious than we realize. The measurement paradox adds yet another layer of strangeness. In quantum mechanics, the act of measurement plays a fundamental role in determining the properties of particles. But measurement requires time and causal relationships. At light speed, where time becomes infinite and causality becomes problematic, the process of measurement itself might break down. This could mean that quantum mechanics, which works perfectly well at ordinary speeds, might fail at light speed. The wave functions that describe quantum particles might never collapse. Quantum superpositions might persist indefinitely. The boundary between quantum and classical behavior might disappear entirely. Perhaps most troubling is the identity paradox. What makes you you? Is it your memories, your thoughts, your physical body, your consciousness? At light speed, all of these aspects of identity would be subject to infinite time dilation and length contraction. Your body would contract to zero length. Your thoughts would be frozen in time. Your memories would be suspended indefinitely. If you somehow survived a journey at light speed and returned to normal speeds, would you still be the same person? Would the infinite transformations of space-time at light speed preserve your identity or destroy it completely? These questions touch on the deepest philosophical issues of personal identity and consciousness. The energy-momentum paradox provides another perspective on the impossibility of light-speed travel. As an object approaches light speed, its energy and momentum both approach infinity. But infinite energy and momentum are not just practically impossible to achieve, they are logically problematic concepts. Infinity is not a number, but a mathematical concept, representing something without bound or limit. Physical systems with infinite energy would have infinite gravitational effects, potentially collapsing the entire universe into a black hole. The paradox suggests that nature must prevent infinite energies from occurring in physical systems. Yet photons, which have no mass, travel at light speed without creating these paradoxes. They have finite energy and momentum, despite traveling at the cosmic speed limit. This suggests that masslessness is not just a technical detail, but a fundamental requirement for light speed travel. Only by having zero rest mass can particles avoid the infinities that plague massive objects at light speed. The observation paradox presents a final layer of complexity. How could you observe the universe around you during light speed travel? Light from distant objects would need time to reach your eyes, but if you are traveling at light speed, you are traveling at the same speed as light itself. Light from ahead of you could never catch up to reach your eyes. Light from behind you would be infinitely red-shifted and effectively invisible. From your perspective, the universe might appear completely dark, except for a narrow cone of incredibly blue-shifted radiation directly ahead. Or perhaps the normal processes of vision would break down entirely at light speed, leaving you unable to observe anything at all. The very act of perception might be impossible at the cosmic speed limit. These paradoxes reveal that light speed is not just a very high velocity, but a fundamental boundary where the normal rules of physics break down. The infinities that appear in the mathematics are not mere technical problems, but signals that we are approaching a realm where space, time, matter, energy, and consciousness itself might be transformed beyond recognition. The paradoxes of light speed travel remind us that the universe operates according to principles that transcend our everyday experience and intuition. They suggest that some boundaries might be absolute, built into the very structure of reality itself. Yet they also inspire us to think more deeply about the nature of existence and to question our most basic assumptions about space, time, and identity. Imagine having the entire cosmos at your fingertips, every star and galaxy within instant reach, every corner of the universe accessible in the blink of an eye. This is the tantalizing possibility that light speed travel seems to offer. If we could somehow overcome the barriers that prevent faster-than-light travel, the implications for exploration and discovery would be beyond anything humanity has ever imagined. The scale of our universe is almost incomprehensibly vast. The nearest star to our Sun, Proxima Centauri, lies 4.25 light-years away. This means that light itself, traveling at the ultimate cosmic speed limit, takes over 4 years to make the journey. With our current technology, a spacecraft would require tens of thousands of years to reach even this closest stellar neighbor. But if we could travel at light speed, this 4-year journey would be transformed into something extraordinary. From the perspective of outside observers, your light speed journey would still take 4 years and 3 months. But from your own perspective, due to the infinite time dilation at light speed, the journey would take no time at all. You would depart Earth and arrive at Proxima Centauri in the same instant. This time compression would apply to journeys of any distance. The center of our Milky Way galaxy lies about 26,000 light-years from Earth. At light speed, this vast distance would collapse to zero from your perspective. You could travel from the outer edge of our galaxy to its central supermassive black hole instantaneously, exploring stellar nurseries, ancient globular clusters, and exotic cosmic phenomena that have never been observed up close. The Andromeda Galaxy, our nearest large galactic neighbor, sits 2.5 million light-years away. This distance is so vast that the light we see from Andromeda tonight left that galaxy when early human ancestors were just beginning to use stone tools. Yet at light speed, even this enormous gulf would be crossed instantaneously from your perspective. You could explore an entirely different galaxy as easily as visiting a neighboring city. The observable universe extends roughly 46 billion light-years in all directions, encompassing hundreds of billions of galaxies, each containing hundreds of billions of stars. At light speed, this entire cosmic expanse would be accessible immediately. You could visit the most distant quasars, explore the cosmic web of dark matter, witness the birth of the first stars, and observe phenomena at the very edge of the observable universe. But what would you actually see during these instantaneous journeys? The experience of light-speed travel would be profoundly different from anything we can imagine based on our everyday experience. As you accelerate toward light speed, the universe around you would undergo dramatic transformations that would alter your perception of space and cosmic structure. Light from objects ahead of you would be blue shifted to higher and higher frequencies as your speed increases. Stars that normally shine with visible light would shift into the ultraviolet, then into X-rays, and finally into gamma rays. The familiar constellations would disappear, replaced by a strange landscape of high-energy radiation invisible to normal human vision. Simultaneously, light from objects behind you would be red-shifted to lower frequencies. Stars would fade from visible light into infrared, then microwaves, and finally radio waves. The rearward view would become increasingly dark as familiar sources of light shifted beyond the range of human perception. As you approach light speed, these effects would become extreme. The entire electromagnetic spectrum would be compressed into a narrow forward-facing cone. All the light, radio waves, X-rays and gamma rays in the universe would appear to stream toward you from directly ahead, creating an intense beam of radiation. The sides and rear of your field of view would become completely dark. At exactly light speed, this compression would become infinite. The entire electromagnetic output of the universe would appear as a single, infinitely intense point of light directly in front of you. This raises serious questions about whether observation would even be possible at light speed. The radiation intensity might be so extreme that it would destroy any normal matter attempting to observe it. The geometry of space itself would also be dramatically altered from your perspective. Length contraction would compress all distances in the direction of your travel towards zero. A spherical star would appear flattened into a disk, then compressed into an increasingly thin sheet. At light speed, all three-dimensional objects would be reduced to two-dimensional projections with no thickness whatsoever. This geometric compression would fundamentally alter your perception of cosmic structure. The vast spaces between stars would shrink to nothing. Entire star systems would be compressed into flat, disk-like arrangements. Galaxies, normally organized as elegant spirals or ellipses, would appear as thin, flat sheets of compressed matter and energy. The experience of exploring different cosmic environments at light speed would be unlike anything we can currently imagine. Consider a journey to the heart of a stellar nursery, like the Orion Nebula. Normally, this region appears as a beautiful, glowing cloud of gas and dust where new stars are being born. But at light speed, the three-dimensional structure of the nebula would collapse into a flat projection. The newborn stars, normally scattered throughout the nebula volume, would appear compressed into a thin sheet. The shock waves and stellar winds that normally carve complex three-dimensional cavities in the gas would be reduced to flat, geometric patterns. The entire star formation process would be frozen in time, from your perspective, yet compressed into an alien, two-dimensional landscape. A visit to a black hole would present even more extreme challenges for a light-speed explorer. Black holes warp space-time so severely that the normal rules of geometry break down near their event horizons. For a light-speed traveler, already experiencing infinite time dilation and complete length contraction, the additional effects of the black hole's gravity might push physics beyond any recognizable limits. The accretion disk around a black hole, normally a swirling, three-dimensional spiral of superheated matter, would appear as a flat, motionless sheet from your light-speed perspective. The jets of high-energy particles that stream from the black hole's poles would be compressed into thin lines. The chaotic, violent dance of matter falling into the black hole would be frozen into strange geometric patterns. Galaxy exploration at light speed would reveal cosmic structure in completely new ways. The spiral arms of galaxies like our own Milky Way extend across hundreds of thousands of light years and contain billions of stars organized into complex, three-dimensional patterns. But from a light-speed perspective, these grand structures would be compressed into flat, abstract designs. The central bulge of a galaxy, normally a sphere or ellipsoid containing ancient red giant stars, would appear as a flat disk. The spiral arms would be reduced to thin curves with no thickness. The dark matter halo that surrounds every galaxy would be invisible anyway, but its gravitational effects on visible matter would create strange, compressed patterns in the distribution of stars and gas. Exploring clusters of galaxies would present an even grander perspective. Galaxy clusters contain hundreds or thousands of individual galaxies, bound together by gravity across distances of millions of light years. These are some of the largest structures in the universe, representing the cosmic web on its grandest scale. From a light-speed perspective, an entire galaxy cluster would appear as a flat collection of disk-like galaxies arranged in abstract patterns. The hot, X-ray emitting gas that fills the space between galaxies in a cluster would be compressed into thin sheets. The dark matter framework that holds the cluster together would manifest only through its gravitational effects on the flattened, visible matter. But perhaps the most profound aspect of light-speed exploration would be the ability to witness cosmic evolution across vast spans of time. Because light takes time to travel across space, looking out into the universe is equivalent to looking back in time. The farther we can see, the further into the cosmic past we can observe. At light speed, you could potentially chase light from distant objects, traveling alongside photons that left their sources billions of years ago. You might be able to witness the formation of the first galaxies, observe the cosmic dark ages when no stars yet shone, or even approach the cosmic microwave background radiation left over from the Big Bang itself. This time-traveling aspect of light-speed exploration would allow you to observe cosmic evolution in ways that are impossible from any single vantage point. You could watch galaxies form and evolve, see how the cosmic web of dark matter grew over billions of years, and witness the changing chemistry of the universe as successive generations of stars created heavier elements. The practical challenges of light-speed exploration would be enormous, assuming such travel were even possible. How would you navigate when the normal appearance of space is completely transformed? How would you communicate with distant locations when the normal electromagnetic spectrum is compressed beyond recognition? How would you land or dock with objects when their three-dimensional structure has been reduced to flat projections? These challenges highlight the profound alienness of light-speed travel. It would not simply be a faster way of moving through familiar space, but a complete transformation of the experience of space itself. The universe would become a strange, flattened, time-frozen landscape bearing little resemblance to the cosmos we know from our everyday experience. Yet, despite these challenges, the possibility of instantaneous access to the entire universe remains one of the most compelling dreams in all of science fiction and speculative physics. To explore every star system, every galaxy, every cosmic structure in the observable universe would represent the ultimate achievement in exploration and discovery. Light-speed travel would transform humanity from a single-planet species to truly cosmic citizens. We could establish outposts around distant stars, study exotic phenomena like neutron stars and quasars up close, and search for life in environments we can currently only imagine. The entire universe would become our laboratory and our home. Whether such exploration will ever be possible remains one of the greatest open questions in physics and cosmology. The mathematical infinities and physical paradoxes associated with light-speed travel suggest that nature may have built absolute barriers into the structure of space-time itself. Yet the universe has surprised us before with its subtlety and flexibility. Until we know for certain whether light-speed travel is possible, the dream of cosmic exploration at the ultimate speed limit continues to inspire scientists, engineers, and dreamers. It represents the ultimate frontier, the final boundary between the possible and the impossible, between the known and the unknowable. In our imagination, at least, the entire universe remains within reach, waiting to be explored at the speed of light itself. The dream of traveling at the speed of light confronts us with energy requirements so vast and technologies so exotic that they challenge our understanding of what might be physically possible. To appreciate the magnitude of these challenges, we must first understand exactly how much energy would be needed and what kinds of revolutionary technologies might theoretically make such travel conceivable. The energy required to accelerate any object with mass approaches infinity as its speed approaches the speed of light. This is not merely a practical limitation of our current technology, but a fundamental consequence of the structure of space-time itself. To understand why, we must examine how relativistic mass increases with velocity and how this affects the energy requirements for acceleration. Consider accelerating a simple 1 kilogram mass to various fractions of light speed. At 10% of light speed, roughly 30,000 kilometers per second, the kinetic energy required is about 4.5 times 10 to the 15th joules. This is roughly equivalent to the energy released by exploding 100,000 tons of TNT or about 8 times the energy of the atomic bomb dropped on Hiroshima. At 50% of light speed, the energy requirement jumps to approximately 2.6 times 10 to the 16th joules. This is equivalent to the total energy consumption of the entire United States for about 2 months. The energy requirement has increased by nearly 6 times, despite only increasing the speed by a factor of 5. At 90% of light speed, the energy requirement becomes truly astronomical. Accelerating our 1 kilogram mass to this speed would require about 2.3 times 10 to the 17th joules. This is equivalent to the energy output of our sun for approximately 6 seconds, or the total energy consumption of human civilization for several centuries. The pattern becomes clear and terrifying as we approach light speed. At 99% of light speed, the energy requirement increases to over 1.6 times 10 to the 18th joules. At 99.9%, it jumps to over 5 times 10 to the 18th joules. Each step closer to light speed demands exponentially more energy. To reach exactly 100% of light speed would require infinite energy, not just a very large amount of energy, but literally infinite energy. This means that all the energy in the observable universe would not be sufficient to accelerate even a single proton to exactly the speed of light. The mathematics of relativity presents an absolute barrier that cannot be overcome by any conceivable technology. But what if we consider more realistic scenarios? What about accelerating an actual spacecraft with human passengers to high fractions of light speed? A modest interstellar spacecraft might have a mass of 1,000 tons or 1 million kilograms. The energy requirements scale directly with mass, so accelerating this spacecraft would require 1 million times more energy than our 1 kilogram example. To accelerate a 1,000-ton spacecraft to 90% of light speed would require approximately 2.3 times 10 to the 23 joules of energy. This is equivalent to the total energy output of our sun for about 18 hours, or roughly the mass energy contained in 2.5 billion kilograms of matter, converted entirely to energy according to Einstein's famous equation E equals mc squared. These numbers help us understand why conventional propulsion systems are utterly inadequate for light speed travel. Chemical rockets, which have carried humans to the moon, and robotic probes throughout the solar system, derive their energy from chemical reactions. The most energetic chemical reactions release only a few electron volts per atom, which is nowhere near sufficient for relativistic travel. Nuclear fission, the process that powers nuclear reactors and atomic weapons, releases about 200 million electron volts per reaction. This is millions of times more energetic than chemical reactions, but still insufficient for light speed travel. Even perfect conversion of nuclear fission energy to kinetic energy would fall far short of the requirements for relativistic spacecraft. Nuclear fusion, the process that powers the sun and hydrogen bombs, releases even more energy per reaction. The fusion of hydrogen into helium releases about 28 million electron volts per helium nucleus produced. Fusion represents one of the most energetic processes we know how to harness, yet even perfect fusion rockets would be inadequate for true light-speed travel. The most energetic process we know is the complete conversion of matter into energy, as described by Einstein's equation. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy. This process releases about 900 million electron volts per proton mass, making it the most efficient energy source theoretically possible. An antimatter propulsion system could theoretically approach the energy densities needed for high-speed interstellar travel, but even antimatter propulsion faces fundamental limitations when approaching light speed. As the spacecraft's speed increases, more and more of the antimatter's energy goes into increasing the relativistic mass, rather than accelerating the spacecraft further. The rocket equation, which governs all forms of reaction propulsion, presents additional challenges for light speed travel. To reach high speeds, a spacecraft must carry enormous amounts of fuel, which increases its mass, which requires even more fuel, creating a vicious cycle. For light speed travel, the fuel requirements become infinite, regardless of how efficient the propulsion system might be. These limitations have led physicists to consider more exotic propulsion concepts that might circumvent the usual restrictions of rocket propulsion. One of the most famous is the Alcubierre drive, proposed by Mexican physicist Miguel Alcubierre in 1994. This theoretical propulsion system would work by warping space-time itself rather than accelerating the spacecraft through space. The Alcubierre drive would contract space in front of the spacecraft and expand space behind it, creating a bubble of distorted space-time that carries the spacecraft along. The spacecraft itself would remain at rest within this bubble, never actually accelerating or exceeding light speed locally. However, the space around the spacecraft would be moving faster than light, effectively carrying the spacecraft to its destination. Such a drive would avoid the infinite energy requirements of conventional acceleration because the spacecraft never actually approaches light speed relative to its local space-time. The energy would instead be used to manipulate the geometry of space-time itself. Unfortunately, the energy requirements for creating such space-time distortions are still enormous and would require exotic forms of matter with negative energy density. Calculations suggest that an Alcubierre drive capable of faster than light travel would require more energy than the mass energy of Jupiter. More recent refinements of the concept have reduced these energy requirements somewhat, but they still remain far beyond anything we can currently imagine producing. The drive would also require materials with properties that may not exist in nature. Wormholes represent another theoretical approach to faster-than-light travel that might avoid some of the energy problems of conventional acceleration. These hypothetical tunnels through space-time could connect distant regions of the universe, allowing travel between them without crossing the intervening space. A journey through a wormhole might be completed faster than light could travel the same distance through normal space. However, natural wormholes, if they exist at all, would likely be microscopic and highly unstable. They would collapse before anything larger than a subatomic particle could pass through them. Creating artificial wormholes large enough for spacecraft would require manipulating space-time on scales that dwarf even the Alcubierre drive requirements. Keeping such wormholes open and stable would probably require threading them with exotic matter having negative energy density. The total amount of negative energy required might exceed the positive energy content of entire stars. Even if such exotic matter exists, we have no idea how to produce or manipulate it in the quantities needed. Some physicists have speculated about even more exotic possibilities involving the manipulation of fundamental forces or the structure of space itself. String theory suggests that our universe might have additional spatial dimensions beyond the three we experience directly. If we could learn to move through these higher dimensions, we might be able to take shortcuts that effectively allow faster than light travel through our normal three-dimensional space. The quantum vacuum, which appears empty but is actually filled with fluctuating quantum fields, might also offer possibilities for exotic propulsion. Some theories suggest that the vacuum itself has structure and properties that could potentially be manipulated to produce, thrust, or alter the flow of time. However, these ideas remain highly speculative and are not supported by any current experimental evidence. Zero-point energy, the energy present in quantum fields even at absolute zero temperature, has been proposed as a potential source of unlimited energy for space propulsion. If we could harness zero-point energy, we might have access to energy sources that could power even the most exotic propulsion systems. Unfortunately, most physicists believe that zero-point energy cannot be extracted in useful amounts without violating fundamental thermodynamic principles. Even if we solve the energy problems, light-speed travel would present enormous technological challenges. How do you build a spacecraft that can survive the transition to light speed? How do you protect the crew from the intense radiation that would result from the compression of the electromagnetic spectrum? How do you navigate when the normal appearance of space is completely transformed? The structural requirements alone would be unprecedented. As a spacecraft approaches light speed, it experiences enormous stresses due to length, contraction, and the changing geometry of space-time. Every component, from the hull to the life support systems, would need to be designed to function under conditions that have never been tested or even properly calculated. The crew would face biological challenges that we can barely imagine. The infinite time dilation at light speed would effectively stop all biological processes from an outside perspective. How could life continue under such conditions? Would consciousness be possible when time has no meaning? These questions probe the deepest mysteries of biology and consciousness. Communication with Earth would become impossible using conventional methods. Radio signals travel at light speed, so they could never catch up to a light-speed spacecraft. Even if faster-than-light communication were possible, the relativistic effects might make coordination between the spacecraft and Earth extremely difficult. Navigation would require completely new technologies and techniques. The normal appearance of stars and galaxies would be transformed beyond recognition by relativistic effects. Traditional navigation methods based on stellar positions would be useless. New forms of guidance based on gravitational fields or exotic physics might be required. Despite these enormous challenges, the possibility of light-speed travel continues to inspire researchers and engineers around the world. Every year, new theoretical concepts emerge that push the boundaries of what might be possible. While none of these ideas are close to practical implementation, they remind us that the universe often proves more flexible and surprising than our initial assumptions suggest. The energy and technology requirements for light-speed travel represent the ultimate engineering challenge. They push us to the very limits of physics and force us to consider possibilities that seem to belong more in science fiction than science fact. Yet throughout history, seemingly impossible dreams have sometimes become reality through human ingenuity and determination. Whether light-speed travel will ever be achieved remains one of the greatest open questions in science and technology. The mathematical barriers seem absolute, yet the universe has surprised us before. Perhaps the key to unlocking light-speed travel lies not in brute force acceleration, but in understanding and manipulating the fundamental structure of space-time itself. As we stand at the threshold of the 21st century's third decade, the question of whether light-speed travel will ever be possible remains one of the most captivating and controversial topics in physics. The mathematical barriers seem absolute, yet the history of science is filled with seemingly impossible breakthroughs that transformed our understanding of reality. To assess the future prospects for light-speed travel, we must examine both the theoretical foundations that might make it possible and the fundamental limitations that might forever keep it beyond our reach. The current state of physics presents us with a paradox. Einstein's theory of special relativity, confirmed by countless experiments over more than a century, tells us that nothing with mass can reach or exceed the speed of light. The energy requirements become infinite, time dilation becomes infinite, and length contraction reduces objects to zero thickness. These mathematical infinities appear to represent absolute barriers built into the structure of spacetime itself. Yet general relativity, Einstein's theory of gravity, suggests that spacetime is dynamic and malleable. Massive objects warp spacetime, creating the phenomenon we experience as gravity. If spacetime can be curved by mass and energy, perhaps it can be manipulated in more exotic ways to circumvent the speed of light barrier. This possibility has inspired theoretical physicists to explore concepts that might make faster-than-light travel achievable without violating the fundamental principles of relativity. The Alcubierre drive remains the most mathematically rigorous proposal for faster-than-light travel. Unlike conventional propulsion systems that accelerate objects through space, the Alcubierre drive would manipulate spacetime itself. By contracting space in front of a spacecraft and expanding space behind it, the drive could theoretically carry the spacecraft faster than light, without the spacecraft ever locally exceeding light speed. Recent developments in Alcubierre drive research have been encouraging. In 2012, physicist Harold White at NASA's Johnson Space Center proposed modifications to the original Alcubierre design that could significantly reduce the energy requirements. By oscillating the warp bubble and optimizing its geometry, White calculated that the energy requirements might be reduced from the mass energy of Jupiter to something closer to the mass of a small asteroid. While this represents a dramatic improvement, the energy requirements remain enormous by any practical standard. A small asteroid might have a mass of billions of tons, and converting this entirely to energy would still represent a technological challenge far beyond our current capabilities. Moreover, the drive would still require exotic matter with negative energy density, something that may not exist in nature. Experimental research into the Alcubierre drive has begun at several institutions around the world. White and his colleagues at NASA have constructed interferometers designed to detect tiny distortions in spacetime that might be created by laboratory-scale warp field experiments. While no positive results have been reported, the mere fact that such experiments are being conducted represents a significant shift in the scientific community's attitude toward faster-than-light travel research. Wormhole research has also advanced significantly in recent years. Theoretical studies have shown that traversable wormholes, while still requiring exotic matter to remain stable, might be more achievable than previously thought. Some models suggest that quantum effects near the wormhole throat could provide the negative energy needed to keep the wormhole open, eliminating the need for large amounts of exotic matter. The quantum vacuum itself has become a subject of intense study as a potential source of exotic effects that might enable faster than light travel. Laboratory experiments have confirmed that the vacuum is not empty, but filled with quantum fluctuations that have measurable effects on physical systems. The Casimir effect, where two metal plates in vacuum attract each other due to quantum fluctuations, demonstrates that vacuum energy is real and can be manipulated. Some researchers have proposed that careful manipulation of quantum vacuum fluctuations might create regions of negative energy density sufficient to stabilize wormholes or power Alcubierre drives. While these ideas remain highly speculative, they represent a shift from purely theoretical concepts to potentially testable propositions. The field of metamaterials has opened new possibilities for manipulating electromagnetic fields in ways that were previously impossible. Metamaterials with carefully engineered structures can bend light around objects, creating invisibility cloaks, or focus electromagnetic energy in ways that violate conventional expectations. Some researchers have speculated that metamaterials might be used to create the exotic conditions needed for faster than light travel. Quantum entanglement, while it cannot be used to send information faster than light, demonstrates that quantum correlations can exist instantaneously across arbitrary distances. This phenomenon suggests that there might be aspects of reality that transcend the usual limitations of space-time. Some physicists have speculated that a deeper understanding of quantum entanglement might reveal new possibilities for faster-than-light effects. The emerging field of quantum gravity seeks to unify Einstein's general relativity with quantum mechanics. This unification might reveal new physics at the intersection of space-time and quantum theory. Some quantum gravity theories, such as loop quantum gravity and causal dynamical triangulation, suggest that space-time itself might have a discrete, granular structure at the smallest scales. If space-time is fundamentally quantized, there might be ways to exploit this structure for exotic propulsion effects. String theory, which proposes that fundamental particles are tiny vibrating strings in higher dimensional space, offers another potential avenue for faster-than-light travel. If our universe really does have additional spatial dimensions beyond the three we normally experience, it might be possible to take shortcuts through these higher dimensions that effectively allow faster-than-light travel through our normal three-dimensional space. Some string theory models suggest that particles called tachyons, which always travel faster than light, might exist in certain circumstances. While no tachyons have ever been detected, and their existence would create serious causality problems, they represent a theoretical possibility that faster-than-light phenomena might be allowed by the fundamental laws of physics. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, has implications for our understanding of space-time and information transfer. If reality is fundamentally holographic, there might be ways to encode and transmit information that bypass the usual limitations of light-speed communication. While this would not necessarily allow faster-than-light travel of matter, it might enable instantaneous communication across arbitrary distances. Dark energy, the mysterious force causing the expansion of the universe to accelerate, represents another potential avenue for exotic propulsion research. Dark energy appears to have negative pressure, causing space itself to expand at an accelerating rate. If we could understand and harness dark energy, we might be able to create the space-time distortions needed for faster-than-light travel. The possibility that our universe might be part of a larger multiverse also opens speculative possibilities for faster-than-light travel. If multiple universes exist, and if there are ways to travel between them, it might be possible to take shortcuts through other universes that effectively allow faster-than-light travel within our own universe. While such ideas remain purely speculative, they illustrate the breadth of possibilities that future physics might reveal. Advanced artificial intelligence might play a crucial role in solving the problems of faster-than-light travel. The mathematical complexity of manipulating space-time and creating exotic matter states might require computational capabilities far beyond current human abilities. AI systems capable of exploring vast parameter spaces and discovering new physical principles might identify solutions that human researchers have overlooked. Nanotechnology and molecular engineering might also contribute to faster-than-light travel research. If exotic matter with negative energy density can be created, it might require atomic-scale precision in its construction and manipulation. Advanced nanotechnology might enable the creation of materials with properties that are impossible to achieve using conventional manufacturing techniques. The development of fusion, power, and antimatter production could provide the enormous energy sources needed for exotic propulsion research. While fusion and antimatter are insufficient for direct light-speed acceleration, they might provide the power needed to operate Alcubierre drives or create and manipulate wormholes. The transition to abundant clean energy might be a prerequisite for serious faster-than-light travel research. However, there are also reasons to believe that light-speed travel might be fundamentally impossible. The mathematical infinities that appear in relativity might represent genuine physical barriers rather than mere technical challenges. The principle of causality, which requires that causes precede their effects, might be so fundamental to the structure of reality that faster-than-light travel is absolutely prohibited. Some physicists argue that any attempt to achieve faster-than-light travel would inevitably lead to logical paradoxes that would make the universe inconsistent with itself. The grandfather paradox and other temporal paradoxes might represent fundamental limitations that prevent faster-than-light travel from ever being achieved, regardless of technological advancement. The holographic principle and other developments in theoretical physics might actually reinforce the impossibility of faster-than-light travel. If information is the fundamental constituent of reality, and if information transfer is limited by the speed of light, then faster-than-light travel might violate the basic structure of existence itself. Quantum mechanics introduces additional complications through the uncertainty principle and the measurement problem. The act of observing or measuring quantum systems affects their behavior in fundamental ways. At the extreme conditions needed for faster-than-light travel, quantum effects might dominate, making it impossible to control or predict the behavior of exotic propulsion systems. The second law of thermodynamics, which requires that entropy always increases in isolated systems, might also present insurmountable barriers to faster-than-light travel. Creating regions of negative energy density or manipulating space-time might require decreasing entropy in ways that violate fundamental thermodynamic principles. Despite these potential limitations, the search for faster-than-light travel continues to drive theoretical and experimental research around the world. Even if true light-speed travel proves impossible, the research effort itself has led to important discoveries about the nature of space-time, quantum mechanics, and exotic matter states. Technologies developed for faster-than-light travel research might have applications in other fields, from advanced propulsion systems to quantum computing. The question of whether light-speed travel is possible ultimately depends on discoveries that have not yet been made. Our current understanding of physics, while remarkably successful, is certainly incomplete. Dark matter and dark energy, which together comprise 95% of the universe, remain mysterious. Quantum gravity remains unsolved. The nature of consciousness and information is poorly understood. Any of these gaps in our knowledge might hide the key to faster-than-light travel. The history of physics is filled with revolutionary discoveries that overturned previous assumptions about what was possible. The quantum revolution of the early 20th century revealed that reality at its smallest scales behaves in ways that seem to violate common sense. Perhaps similar revolutions await us in our understanding of space-time and faster-than-light phenomena. Whether humanity will ever achieve light-speed travel remains one of the greatest open questions in science. The mathematical barriers seem formidable, but the universe has surprised us before with its flexibility and hidden possibilities. As we continue to probe the deepest mysteries of space, time, and matter, we move closer to answering this fundamental question about the ultimate limits of exploration and discovery. Of all the questions surrounding light-speed travel, perhaps none is more fascinating or mysterious than what you would actually experience during such an impossible journey. Would you feel the universe rushing past you at incredible speed? Would time seem to stop? Would you be aware of anything at all? The answers lead us into some of the strangest territory in all of physics, where our normal concepts of consciousness, perception, and existence itself begin to break down. To understand what light-speed travel might feel like, we must first consider how your experience would change as you gradually accelerate toward this cosmic speed limit. At ordinary speeds, acceleration creates familiar sensations. You feel pressed back into your seat when a car accelerates, or experience weightlessness when an elevator begins to fall. These sensations arise because your body must adjust to changes in velocity. But as you approach significant fractions of light speed, the experience would become increasingly alien. At 50% of light speed, time dilation would begin to affect your perception in subtle ways. Your biological processes would slow down relative to outside observers, but you would not notice this directly. Your heartbeat, breathing, and neural activity would all proceed at their normal subjective pace. What you might notice, however, is how the universe around you begins to transform. Stars ahead of you would start to shift toward the blue end of the spectrum as their light becomes compressed by your motion. Stars behind you would shift toward red. The familiar constellations would begin to change color and apparent position as relativistic effects altered your perception of the cosmos. As your speed increases to 90% of light speed, these effects would become dramatic. The Doppler shifting of starlight would be so extreme that many stars would disappear from visible light entirely. Those ahead would shift into ultraviolet and beyond, while those behind would fade into infrared and radio waves. The night sky would become an alien landscape of unfamiliar colors and patterns. Time dilation would also begin to create noticeable effects when you compare your experience to the outside world. If you could somehow observe Earth during your journey, you would see everything there happening in fast forward. Years would pass on Earth while you experienced only months. Seasons would change rapidly, and the slow processes of geological and biological evolution would appear accelerated. But the most profound changes would occur as you approach the speed of light itself. At 99% of light speed, time dilation becomes so extreme that decades pass on Earth for every year you experience. The blue shifted radiation ahead of you becomes incredibly intense, while the universe behind you fades into near darkness. All the electromagnetic energy in the universe appears to compress into a narrow cone directly ahead. At 99.9% of light speed, you would be entering a realm where physics becomes increasingly exotic. Time dilation approaches factors of hundreds or thousands. The entire electromagnetic spectrum ahead of you compresses into an impossibly intense beam of radiation. Length contraction begins to noticeably flatten the three-dimensional structure of space around you. As you approach exactly the speed of light, something truly extraordinary happens to the nature of experience itself. Time dilation approaches infinity, meaning that infinite time passes in the outside universe for every moment you experience. From the perspective of outside observers, your time essentially stops. You become frozen in a single instant that lasts forever. But what would this infinite time dilation feel like from your perspective? Here we encounter one of the deepest mysteries in all of physics. If your biological processes slow down by an infinite factor, can consciousness continue to exist? Can you think, feel, or experience anything when time has no meaning? One possibility is that consciousness would simply cease at light speed. The neural processes that support awareness require time to function. Thoughts must unfold in temporal sequence. Memories must form and be accessed across time intervals. Without the flow of time, the very mechanisms of consciousness might shut down completely. Another possibility is that consciousness would be transformed into something completely alien to our normal experience. Perhaps at light speed, awareness would exist in a timeless state where all thoughts and experiences occur simultaneously. Past, present, and future might merge into a single eternal moment of consciousness. Length contraction presents additional challenges for understanding light speed experience. As you approach light speed, your body would contract to zero thickness in the direction of motion from the perspective of outside observers. But what would this feel like to you? Would you be aware of becoming infinitely thin, or would your contracted measuring devices make everything seem normal? The compression of space around you would also dramatically alter your perception of the universe. Distances in the direction of your travel would shrink towards zero. A journey to the nearest star, normally over 4 light-years long, would become a journey of zero distance from your perspective. The entire universe would collapse into a flat projection with no depth. This raises profound questions about the nature of spatial perception at light speed. How do you navigate through space when space has no extension in the direction you are traveling? How do you perceive three-dimensional objects when they have been compressed into two-dimensional sheets? The normal experience of moving through space might become completely meaningless. The electromagnetic spectrum would also be transformed beyond recognition. All the light, radio waves, X-rays, and gamma rays in the universe would appear compressed into a single, infinitely intense point directly ahead of you. The normal rainbow of colors would disappear, replaced by this overwhelming concentration of all electromagnetic energy. This electromagnetic compression might make observation impossible. The intensity of radiation streaming toward you might be so extreme that it would instantly destroy any normal matter attempting to detect it. You might exist in a state where perception is physically impossible, cut off from any sensory contact with the universe around you. From your light-speed perspective, every journey would be instantaneous. No matter how far your destination, length contraction would reduce the distance to zero. You would depart and arrive in the same moment, experiencing no passage of time during even the longest cosmic voyages. The entire observable universe would be accessible without any subjective travel time. This instantaneous travel creates fascinating paradoxes about the nature of experience. If every journey takes zero time, when do you experience traveling? Do you exist in a state of eternal departure and arrival? Or do the concepts of departure and arrival lose all meaning when time and space have been reduced to mathematical singularities? The experience of light speed might also involve a complete transformation of identity itself. Your memories, formed over years of experience, would be compressed into a timeless state. Your personality, shaped by temporal sequences of events, might no longer have any coherent structure. The very sense of being a continuous self, existing through time, might disappear. Perhaps at light speed, individual consciousness would merge with something larger and more universal. If time stops and space collapses, the usual boundaries between self and universe might dissolve. You might experience a kind of cosmic consciousness where individual identity expands to encompass all of space and time. This connects to deep philosophical questions about the relationship between consciousness and physical reality. Is consciousness necessarily tied to the flow of time and the extension of space? Can awareness exist independently of the usual structures of space-time? Light-speed travel pushes these questions to their absolute limits. The return from light speed might be equally mysterious. If you somehow survived the transition to light speed and then decelerated back to normal speeds, would your consciousness remain intact? Would your memories of the light speed experience be coherent, or would they be fundamentally incomprehensible to a mind operating in normal space-time? You might return with memories of experiencing infinite time in a single moment, or of seeing the entire universe compressed into a point of light. Such memories might be impossible to integrate into normal consciousness, leaving you fundamentally changed by the encounter with the cosmic speed limit. The biological effects of light-speed travel would add another layer of complexity to the experience. Every cell in your body, every molecule, every atom would be subject to the same extreme relativistic effects. The normal chemical processes that sustain life might be impossible under such conditions, raising questions about whether biological consciousness could survive at all. Perhaps the most profound aspect of light-speed experience would be the encounter with infinity itself. At light speed, mathematical infinities become physical realities. Time dilation becomes infinite. Energy requirements become infinite. Length contraction becomes complete. You would be experiencing conditions where the normal rules of mathematics and physics break down. This encounter with infinity might represent a transition to a completely different mode of existence. Instead of being a finite being traveling through space-time, you might become something more like a mathematical abstraction, existing in a realm where the usual distinctions between possible and impossible have no meaning. The light speed experience might also connect you to the fundamental nature of light itself. Photons, the particles of light, exist naturally at light speed and experience no passage of time during their journeys across the cosmos. A photon created in the heart of a distant star experiences no time during its billion-year journey to Earth. Perhaps at light speed, you would share in this timeless existence of light. From a photon's perspective, if such a term has meaning, the entire history of the universe occurs in a single instant. The Big Bang, the formation of galaxies, the evolution of life, and the ultimate fate of the cosmos all happen simultaneously. Light-speed travel might give you access to this cosmic perspective where all of time and space are present at once. Whether consciousness could survive such an experience remains one of the deepest mysteries surrounding light-speed travel. The transformation might be so complete that the being who returns would bear little resemblance to the one who departed. You might become something entirely new, a conscious entity adapted to existence at the cosmic speed limit. Understanding what you would experience at light speed requires us to question our most basic assumptions about consciousness, time, space, and identity. It pushes us to the very edge of what might be comprehensible to minds that evolved in a world of ordinary speeds and familiar space-time. The light-speed experience might be the ultimate frontier, not just of physics, but of consciousness itself. We arrive now at the ultimate question, the final destination of our impossible journey through the cosmic speed limit. What happens at the precise moment when you reach the speed of light itself? This moment represents more than just the achievement of maximum velocity. It is the point where the familiar laws of physics dissolve into mathematical infinities, where time and space lose their ordinary meaning, and where the very nature of existence might be transformed beyond recognition. The transition to exactly light speed represents a boundary between two fundamentally different realms of reality. On one side lies the universe we know, where time flows forward, space has extension, and objects have finite mass and energy. On the other side lies a realm where these familiar concepts break down completely, replaced by infinities and paradoxes that challenge our deepest understanding of what it means to exist. As you approach this boundary, the changes in your experience become increasingly dramatic. At 99.999% of light speed, time dilation has become so extreme that millions of years pass in the outside universe for every second you experience. The entire electromagnetic output of the cosmos compresses into an infinitely narrow beam directly ahead of you. Space contracts so severely that the distance to the most remote galaxies approaches zero. But what happens when you take that final step and reach exactly 100% of light speed? The mathematics of relativity provides some clues, though they lead to conclusions that seem to violate our basic understanding of reality. At light speed, time dilation becomes truly infinite. This means that infinite time passes in the outside universe for every moment of your existence. From the perspective of outside observers, you would become frozen in time at the moment you reach light speed. Your clocks would stop ticking. Your biological processes would cease. You would become a static, unchanging object, suspended in a single instant that lasts forever. To the rest of the universe, you would have effectively left the normal flow of time entirely. But this raises a profound paradox. If infinite time passes in the outside universe while you exist in a single moment, what happens to the universe itself during this infinite period? Stars would exhaust their fuel and die. Galaxies would drift apart as cosmic expansion carries them beyond each other's gravitational reach. Protons would decay, black holes would evaporate through Hawking radiation, and the universe would approach its ultimate heat death. All of this cosmic evolution would occur while you remain frozen at light speed. You would witness, in some sense, the entire future history of the universe compressed into the single moment of reaching light speed. The birth and death of countless stars, the formation and dissolution of galaxies, and the ultimate fate of all matter and energy would unfold around your motionless form. Yet from your own perspective, the experience would be completely different. Due to infinite time dilation, your journey to light speed would take no subjective time at all. You would transition from 99.999% of light speed to 100% instantaneously, without experiencing any passage of time during the acceleration. This creates an extraordinary paradox. The same event, reaching light speed, would simultaneously take infinite time and zero time depending on who observes it. This contradiction suggests that the concept of reaching light speed might not be physically meaningful. Perhaps the mathematics is telling us that the transition to exactly light speed is not an event that can actually occur in our universe. Length contraction presents equally mind-bending implications. As you reach light speed, your body would contract to exactly zero thickness in the direction of motion. You would become a two-dimensional projection with no extension whatsoever along your direction of travel. In a very real sense, you would cease to exist as a three-dimensional object. This complete length contraction raises fundamental questions about identity and continuity. Are you still the same person when your three-dimensional body has been reduced to a two-dimensional sheet? Can consciousness exist in a being with zero thickness? The very concept of physical existence seems to break down when spatial extension disappears entirely. The energy requirements for reaching light speed also become infinite at this boundary. According to Einstein's equations, accelerating any massive object to exactly light speed would require infinite energy. This is not just a practical limitation, but a fundamental prohibition built into the structure of space-time itself. The universe seems designed to prevent massive objects from ever achieving this ultimate speed. This infinite energy requirement suggests that the act of reaching light speed might involve a transformation so profound that it transcends the usual categories of physics. Perhaps reaching light speed does not mean continuing to exist as a massive object moving very quickly. Perhaps it means transformation into something entirely different, something that exists in a realm beyond mass, energy, and ordinary space-time. The electromagnetic effects at light speed also reach their ultimate extreme. All the electromagnetic radiation in the universe would appear compressed into a single point of infinite intensity directly ahead of you. This represents not just the sum of all starlight, but all radio waves, microwaves, X-rays, gamma rays, and every other form of electromagnetic energy that exists. The intensity of this compressed radiation would be so extreme that it might fundamentally alter the structure of space-time itself. Some physicists speculate that such intense electromagnetic fields could create black holes, wormholes, or other exotic space-time geometries. The very act of reaching light speed might tear holes in the fabric of reality. This leads to speculation that reaching light speed might not be an ending but a transformation into a completely different mode of existence. Instead of continuing to travel through normal space-time, you might transition into a realm where the usual laws of physics no longer apply. You might become something like a living piece of space-time geometry, existing as a conscious distortion in the fabric of reality itself. The quantum mechanical aspects of light speed also present fascinating possibilities. In quantum mechanics, particles can exist in superposition states where they have multiple properties simultaneously until they are observed. At light speed, where the normal flow of time stops, quantum superpositions might never collapse. You might exist in a state where all possible outcomes occur simultaneously. This quantum perspective suggests that reaching light speed might not lead to a single, definite outcome, but to a superposition of all possible outcomes. You might simultaneously exist and not exist, be conscious and unconscious, travel and remain stationary. The act of reaching light speed might create a quantum state that transcends the usual binary categories of existence. From this quantum perspective, the question of what happens when you reach light speed might not have a single answer. Instead, reaching light speed might create a branching point where all possible futures occur simultaneously. You might enter a realm of infinite possibility where every conceivable outcome becomes equally real. The thermodynamic implications of reaching light speed also point toward fundamental transformations. Thermodynamics requires that entropy always increases in isolated systems, leading toward maximum disorder and heat death. But at light speed, where time becomes infinite, the usual thermodynamic processes might break down entirely. Perhaps reaching light speed allows escape from the normal constraints of thermodynamics. Instead of being subject to increasing entropy and eventual heat death, you might enter a state where thermodynamic laws no longer apply. This could represent a form of immortality that transcends the usual physical limitations of existence. Some physicists have speculated that consciousness itself might be the key to understanding what happens at light speed. If consciousness is fundamentally information-based, and if information can exist independently of matter and energy, then perhaps consciousness could survive the transition to light speed even if the physical body cannot. This leads to the possibility that reaching light speed might represent the ultimate evolution of consciousness. Instead of being trapped in a physical body, subject to the limitations of space-time, consciousness might become pure information, capable of existing at light speed. You might become a conscious entity made of light itself, sharing in the timeless existence of photons. The connection between consciousness and light becomes particularly intriguing when we consider that light is the medium through which we perceive the universe. Everything we see, from nearby objects to distant galaxies comes to us through light. Perhaps reaching light speed allows consciousness to merge with this fundamental medium of perception, becoming one with the light that carries information throughout the cosmos. This merger with light might represent the ultimate form of cosmic consciousness. Instead of being a localized awareness trapped in a single location, you might become a distributed consciousness that exists wherever light travels. You could be simultaneously present at every star, every galaxy, every corner of the universe that light has ever reached. The philosophical implications of reaching light speed extend beyond physics into the deepest questions about the nature of reality itself. If reaching light speed is possible, it suggests that the universe contains realms of existence that transcend our ordinary experience. It implies that consciousness might be more fundamental than matter and energy, capable of existing in states that defy our usual understanding. But perhaps the most profound implication is that reaching light speed might not be an ending at all, but a beginning. Instead of representing the ultimate speed limit, light speed might be the threshold to entirely new forms of existence and experience. Just as breaking the sound barrier opened new possibilities for flight, breaking the light barrier might open new possibilities for consciousness and life itself. The question of what happens when you reach light speed ultimately remains unanswered because it pushes us beyond the boundaries of current physics and into pure speculation. The mathematical infinities that appear in the equations might represent genuine physical impossibilities, or they might be signs that our current understanding is incomplete. Whether reaching light speed represents the ultimate transformation of consciousness, the dissolution into pure energy, or simply an impossibility built into the structure of reality itself, the question continues to inspire scientists and philosophers to probe the deepest mysteries of existence. In contemplating this ultimate boundary, we are forced to confront fundamental questions about the nature of time, space, consciousness, and reality itself. Perhaps the journey toward light speed is more important than the destination. In pushing against this cosmic speed limit, we expand our understanding of the universe and our place within it. We discover new physics, develop new technologies, and gain new perspectives on the nature of existence. Whether we ever reach light speed or not, the attempt to understand this ultimate boundary continues to drive human knowledge toward ever greater depths of understanding and wonder. As our journey through the realm of light speed travel draws to a close, we find ourselves standing at the edge of human understanding, gazing into mysteries that may forever remain beyond our complete comprehension. We have explored what it might mean to travel at the ultimate cosmic speed limit, encountering paradoxes and possibilities that challenge our most fundamental assumptions about reality itself. Throughout this exploration, we have discovered that the speed of light is far more than just a very high velocity. It is woven into the very fabric of existence, connecting space and time, matter and energy, cause and effect, in ways that define the structure of our universe. The speed of light sets the boundaries of what is possible and what remains eternally beyond our reach. We have seen how time itself becomes malleable at high speeds, stretching and dilating until it approaches infinity at light speed. The steady tick of clocks that marks our everyday existence transforms into something alien and mysterious when we approach the cosmic speed limit. Time, which seems so absolute and universal in our daily experience, reveals itself to be relative and flexible, dependent on motion through space. Space, too, shows its true nature as we approach light speed. The familiar three dimensions that define our world contract and compress until they disappear entirely at the ultimate velocity. The vast distances between stars and galaxies shrink to nothing, and the entire universe collapses into a flat projection with no depth or extension. Space and time, which seem so separate and distinct in everyday life, merge into a unified space-time that bends and warps in response to motion and energy. The energy requirements for light-speed travel have shown us the profound barriers that nature has built into the cosmic speed limit. The infinite energy needed to accelerate any massive object to light speed represents more than a technological challenge. It is a fundamental prohibition written into the laws of physics themselves. Yet this same limitation has inspired us to imagine exotic technologies and revolutionary concepts that push the boundaries of what might be possible. We have encountered paradoxes that seem to make light-speed travel logically impossible. The twin paradox, causality violations, and temporal contradictions all suggest that the universe protects itself against actions that would threaten the logical consistency of reality. These paradoxes remind us that the speed of light is not just a speed limit, but a guardian of the rational structure of existence itself. The exploration of what you might experience at light speed has taken us to the very edge of consciousness and identity. We have questioned whether awareness can exist when time has no meaning, whether consciousness can survive when the physical body contracts to zero thickness, and whether individual identity can persist through such profound transformations. These questions probe the deepest mysteries of mind and existence. Perhaps most remarkably, we have discovered that the journey toward light speed might be more important than reaching the destination itself. The attempt to understand and achieve light speed travel has driven advances in physics, technology, and our understanding of the cosmos. Even if light speed travel proves impossible, the pursuit of this ultimate goal continues to expand human knowledge and capability. The mathematics of light speed travel, with its infinities and singularities, points toward realms of physics that we do not yet understand. These mathematical barriers might represent genuine impossibilities, or they might be signs that our current theories are incomplete. The history of science suggests that seemingly impossible barriers sometimes yield to new understanding and revolutionary insights. We stand today much as our ancestors stood when they looked up at birds and dreamed of flight, or gazed at the moon and imagined walking on its surface. What seemed impossible to them became routine achievements for later generations. Perhaps light-speed travel, which seems impossible to us today, will become achievable for future humans armed with deeper understanding and more advanced technology. The universe has consistently surprised us with its subtlety and flexibility. Quantum mechanics revealed that reality at its smallest scales operates according to principles that seem to violate common sense. General relativity showed us that space and time are dynamic and malleable, capable of being warped by mass and energy. Who knows what future discoveries might reveal about the nature of space-time and the possibilities for faster-than-light travel. Even if true light-speed travel remains forever impossible, the exploration of this cosmic boundary has enriched our understanding of the universe in countless ways. We have learned about the deep connections between space and time, discovered the relative nature of simultaneity, and explored the profound implications of Einstein's insights about the structure of reality. The speed of light serves as a constant reminder of both the vastness and the limitations of our cosmic environment. It connects us to every corner of the universe, while simultaneously defining what regions of space-time we can influence and what information we can receive. In a very real sense, the speed of light defines the boundaries of our cosmic neighborhood and determines how we experience the passage of cosmic time. Looking toward the future, the quest to understand and perhaps achieve light-speed travel continues to inspire new generations of scientists, engineers, and dreamers. Research into exotic matter, space-time manipulation, and quantum gravity might eventually reveal pathways around the apparent barriers to faster-than-light travel. Advanced artificial intelligence and nanotechnology might enable us to explore possibilities that are currently beyond human capability. The search for extraterrestrial intelligence takes on new meaning when we consider the limitations imposed by light speed. If alien civilizations exist elsewhere in the galaxy, they face the same cosmic speed limit that constrains our own expansion into space. The vast distances between stars, measured in years even for light itself, represent barriers that any spacefaring civilization must confront. Perhaps the solution to interstellar travel lies not in overcoming the speed of light, but in learning to work within its constraints. Generation ships that take centuries to reach their destinations, hibernation technologies that allow travelers to sleep through long journeys, or robotic probes that can survive the vast emptiness between stars might represent more realistic approaches to exploring the galaxy. The speed of light also reminds us of our place in the cosmic timeline. The light from distant galaxies carries information about the universe as it was billions of years ago, allowing us to observe cosmic history directly. We are connected to every era of cosmic evolution through the light that has traveled across space and time to reach us. In studying the cosmos, we are literally looking into the past and witnessing the story of existence itself. This connection between light speed and cosmic time gives us a unique perspective on our place in the universe. We exist at a moment in cosmic history when the universe is still young enough for stars to shine and galaxies to form, yet old enough for complexity and life to emerge. The light that reaches us tonight left distant sources when the universe was very different from what it is today. As we contemplate the limits imposed by the speed of light, we are reminded that the universe operates according to principles that transcend human desires and ambitions. The cosmic speed limit represents a fundamental aspect of reality that exists independently of our wishes to overcome it. Yet this same limit has shaped the universe in ways that made our existence possible. The finite speed of light allowed regions of the early universe to evolve independently, creating the diversity of structures we observe today. If information could travel instantly across any distance, the universe might have evolved into a uniform, featureless expanse, lacking the complexity necessary for life. The speed of light barrier might be one of the cosmic conditions that enabled consciousness to emerge and contemplate its own existence. In the end, our exploration of light speed travel brings us face to face with the deepest mysteries of existence. We discover that reality is far stranger and more wonderful than our everyday experience suggests. Space and time, which seem so solid and reliable, are revealed to be flexible and relative. Matter and energy, which appear separate and distinct, prove to be different aspects of a deeper unity. The speed of light stands as a monument to the elegance and mystery of the cosmic order. It represents both a barrier and an inspiration, a limit that defines what is possible while challenging us to imagine what might lie beyond. Whether we ever achieve light speed travel or not, the pursuit of this ultimate goal continues to drive human curiosity and creativity toward ever greater understanding of the cosmos and our place within it. As we drift towards sleep, carried along by the gentle flow of cosmic time, we can marvel at the fact that we live in a universe where such profound questions can be asked and explored. The speed of light may forever remain beyond our reach, but it will never cease to inspire us to push the boundaries of knowledge and to dream of what might be possible in this vast and mysterious cosmos that we call home.